Imagine you're tearing down the highway at 70 miles per hour. Inside your car, there's a hidden, high-stakes battlefield of data. You've got dozens of microcontrollers running the brakes, the engine, the steering, even the windows, and they are all demanding attention at the exact same microsecond. The stakes here literally could not be higher. Think about it. If your anti-lock braking system's critical message gets delayed just because, say, a passenger decided to roll down their window, that's a catastrophic failure. I'm your host, and today we are going to master exactly how automotive networks prevent this kind of disaster.
So let's look at the macro-level mystery of the modern vehicle's nervous system. You've got over 50 computers all wired together on the same bus, essentially shouting over one another simultaneously. Now, in early networking systems, if two nodes transmitted at once, the data physically collided on the wire and was completely destroyed. The nodes would realize there was a collision, wait some random amount of time, and try again. But remember, a car traveling at 70 miles per hour, it simply doesn't have time for a retry.
So, the crucial question we have to answer is this. How on earth do 50-plus computers talk on one single wire at the exact same time without instantly crashing the network? Well, by the end of this explainer, you are going to master the physical and mathematical intuition behind how the controller area network, the CAN bus, solves this problem flawlessly every single time.
Here's our roadmap for today. We'll start with 1, the CAN arbitration mystery. Then we'll cover 2, the physics of priority, followed by 3, bit-by-bit collision resolution. We'll put it into practice in 4, the walkthrough example. Avoid a major trap in 5, the oscilloscope polarity gotcha, and wrap up with 6 critical takeaways.
All right, let's dive straight into Section 1, the CAN arbitration mystery.
To really understand how this works, we need to zoom way past the macro vehicle level, right down to the microscopic atomic level of the voltage on the network wires. The CAN protocol relies on a concept called CSMA/CR. That stands for Carrier Sense Multiple Access with Collision Resolution. I want you to focus heavily on that last part, collision resolution, as a non-destructive method. Unlike those older protocols where simultaneous transmission completely corrupts the signal, CAN ensures the highest priority message cleanly wins access without ever destroying its own data. But how is a non-destructive collision even physically possible?
That brings us to Section 2, the physics of priority.
The answer actually lies in the fundamental physical layer of the network itself, which relies on 2 distinct states: dominant bits and recessive bits. Now, I want you to use this visual analogy and never ever forget it. Imagine a pitch-black room filled with people, and they're all holding flashlights. A recessive bit is a turned-off flashlight. A dominant bit is a turned-on flashlight. If everyone in the room transmits a recessive bit, well, the room just stays dark. But if even one single person clicks on their dominant flashlight, the entire room instantly becomes bright. The dominant state literally, physically overwrites the recessive state.
Let's look at the actual mathematical expression governing this physical layer on the wire. The state of the bus is determined by the differential voltage, written as delta U equals U CAN N minus U CAN L. Here, U CAN H and U CAN L are the absolute voltages on the high and low CAN wires, measured relative to ground. When a node transmits a dominant bit, which is a logical 0, it physically drives those two wires apart, forcing the differential voltage, that delta U, to approximately 2 volts. But when transmitting a recessive bit, a logical 1, the node essentially just lets go of the wires, leaving the differential at 0 volts. Think about it. If node A is essentially sending 0 volts and node B forces 2 volts, the bus physically reads 2 volts. Dominant absolutely always wins.
Moving right along to Section 3, bit-by-bit collision resolution.
So we know the physical rules of the wire now, but how do the microcontrollers actually use this physics to decide priority in real time? Well, before a node transmits, it listens to check if the bus is free. If it is, it sends a dominant start-of-frame bit, and then starts firing off its message identifier, bit by bit. But here is the absolute genius of the protocol. As the node transmits each individual bit onto the wire, it simultaneously reads the voltage back from the wire to see what state the bus actually is in.
This leads us right to the golden rule of CAN arbitration, and it's 3 simple steps. Step 1, transmit your bit. Step 2, read the bit back from the bus. Step 3, if you transmit a recessive bit, a logical 1, acting like a turned-off flashlight, but you read a dominant bit back from the bus, a logical 0, sensing the room is suddenly bright, you stop immediately. You have lost arbitration, and you instantly switch from a transmitter to a receiver.
Let's see this in action in Section 4, the walkthrough example.
We're going to put this into practice with a methodical, high-stakes showdown.
Imagine 3 nodes trying to transmit at the exact same microsecond. We've got node 1 with ID 301, node 2 with ID 303, and node 3 with ID 300. Remember, a binary 0 is our dominant, turned-on flashlight. All 3 nodes send their first bits perfectly in sync. Scanning left to right, they all send 001, then 0010, then 11. For the first 9 bits, they are perfectly matched, fighting neck and neck. But look at the 10th bit. Node 2 tries to send a recessive 1, while nodes 1 and 3 send a dominant 0. Node 2 reads that 0 on the bus, realizes its flashlight was just overpowered, and it instantly drops out of the race.
So now it's just a head-to-head showdown between node 1 and node 3. Moving to the 11th and final bit of the identifier, node 1 tries to send a recessive 1, but node 3 sends a dominant 0. That dominant 0 physically overwrites the bus. Node 1 reads the wire, sees the 0 it definitely didn't send, and it has to drop out. Node 3 wins arbitration and just keeps right on transmitting its data completely uninterrupted. Because 0 is dominant, the node with the lowest numerical ID always has the highest priority.
Which brings us to Section 5, the oscilloscope polarity gotcha. Now, the math and logic here are honestly beautiful, but when engineers actually try to measure this in the real world, they very often fall into a massive trap. Here we see a standard physical test setup. We have our 3 microcontrollers hooked up to transceivers. To see the physical arbitration actually happening, we use an oscilloscope with a differential probe across the CAN high and CAN low lines. This probe is physically measuring that exact delta U we derived earlier.
In the resulting oscilloscope traces, if you analyze the individual transmit pins, it reveals a super clear progression. You can physically watch all 3 nodes start together until the signals for nodes 1 and 2 just go flat as they lose arbitration and drop out. The overall differential voltage on the bus itself perfectly matches the surviving node 3's transmission. It's a clean victory. But pay very close attention to the voltage scale on that trace.
Here's the gotcha that trips people up. Mathematically, as we proved, a dominant bit should result in a delta U of positive 2 volts. But in the source documentation's oscilloscope capture, the dominant level is clearly shown as negative 2 volts. Why? Because the polarity of the differential probe was intentionally swapped. They do this so the visual shape of the bus waveform perfectly matches the logic level seen at the transmit and receive pins of the microcontroller. It's basically a visual trick to make logic debugging easier. But if you don't know your probe orientation, the physical math will look completely backwards, and it will absolutely confuse you.
Let's wrap this up with Section 6, Critical Takeaways.
We've gone all the way from the macro vehicle down to the atomic wire, derived the core equations, and successfully solved the collisions. Let's lock in your 3 rapid-fire takeaways. First, the lowest ID always wins because it has more leading dominant zeros. Second, this arbitration is mathematically non-destructive. The winning message is completely untouched and uncorrupted. Third, the physical reality is governed by delta U equals UCANH minus UCANL, where a dominant state physically overwrites a recessive state. Just remember that flashlight taking over the dark room.
I'm going to leave you with this provocative edge case question sourced straight from the text. What happens if a node actually loses arbitration after the arbitration field is already over? It's brutal. It's immediately interpreted as a critical network error, and an error frame is literally blasted onto the bus to intentionally destroy the corrupted data. But we are going to cover that intense error handling in our next breakdown. If you want to master more automotive protocols and survive the absolute trenches of EMC design, hit subscribe and I will see you in the next explainer.